Hey everyone, and welcome back. In this video, we're going to talk about graphing log functions. So without further ado, let's get into the dang thing. Last time we talked about exponentials, which was shown in red, and this time I just want to spend a little bit of time talking about the key features of the graph we see in blue, the logarithm. A logarithm function is either going to look like this, looks like we had, just like we had exponential growth, or our logarithm function can actually look a little something like this, which is a little weird, depending on if we had like a decay function. And the reason that it kind of looks like this is exponentials and logs are inverses. And if they're inverses, x and y is swapped. So they're reflected across this line, y equals x. So those are the two type of log functions we're going to be dealing with. This one was like the inverse of a growth function, exponential growth, and this is the inverse of exponential decay. All right. And something we want to talk about still is our original equation. Like our general equation for a logarithm is going to be still y is equal to a, where a is vertical stretch, compression, or reflection across the x-axis. But instead of our base of the exponential being b, we're going to have a logarithm with our base b of some sort of input. I'm going to use the letter a. With x minus our horizontal shift and plus k on the outside representing our vertical shift. So again, the base of the logarithm depends on what our graph is going to look like. And so this is the inverse of growth. That means the base is bigger than 1, which is more often than not what we see for our logarithms. However, just like this, it was decay. If the base is between 0 and 1, we're going to get the inverse of decay. And something you'll notice, no matter what, if I have the inverse growth or the inverse of decay, these graphs also tend to flatten out. They just flatten out in a different way. These graphs tend to flatten out vertically. So both of these graphs are going to have vertical asymptotes where they flatten out. You'll notice that the blue graph on the main guy flattens out at the line 0, and this is a vertical line, so it's an x equals equation. Since we're crossing the x-axis at 0, that's why we have the equation x equals 0. And if you're thinking about a vertical shift left and right, that would affect moving that vertical asymptote. So now the horizontal shift is going to directly affect where your graph flattens out. So the horizontal shift is going to affect our graph. Remember, if we're going to move our graph up and down, that does not affect my vertical asymptote. Put your arm vertically and move it up or down. It's not going anywhere. It's not doing anything crazy. So only shifting left and right is going to affect our values. One other thing. Since they're inverses of each other, we had this point, right? From x was 0, y was 0. We always went anything to the 0 power was 1. Now, logarithms, this one doesn't go through the right point, but pretend it's supposed to go through this point here. Sometimes it's really hard to draw with my stylus. So those points should be flipped. So realistically, this logarithm graph should go through that point right there. So something I want us to make a note of is with exponentials, from the asymptote, you go up 1, right? From these logarithms, from the vertical asymptote, we're going to go right 1 point. Always to the right 1 point. So that's how we're going to make and determine the shape of our graph. Let's get into it. So looking at this logarithm graph, it's definitely a logarithm, and it is flattening out somewhere. So I need to know, where's my asymptote? Where's it flattening out? It's flattening out right here at x is equal to 0. Now remember, that means that there's no left or right shift happening because that would affect our asymptote. And for our parent function, that was right there at 0 as well. Also notice that I did this one correctly. To the right of the asymptote is 1 point. So just like we used base 2 for the original equation, we're going to use log base 2 for this. And since there was no left or right movement, I could just put in plus 0 right there for our equation. And our graph didn't move up or down because that point to the right would have been moved up or down. So we also don't have any up or down movement because this guy is still just to the right one value. If it had been moved up or down, that point would have been right here or something like that. So we know for sure that it was not moved up or down. Now that we have our graph, we can easily explain the domain and range. The domain, the smallest x value, is not negative infinity. Look, we hit a wall. The asymptote stops us from going all the way left. So the smallest x value we have is 0, our asymptote. Our graph does not exist over here on the left-hand side, smaller than 0. There's nothing there. So we have to start at 0 for our domain. But our graph does continue to the right, so it goes all the way till positive infinity, or x is greater than 0. The range is the y values, the smallest y values. Notice that our graph is living large. It's existing. It's going all the way down towards negative infinity. That's fine. So our range goes from negative infinity, and then it looks like it's going to stop our graph. But realistically, this thing just keeps going and going and going. It's kind of like a square root function. There's nothing stopping this. Nothing at all is stopping this. And the reason for that is because these are inverses. So the exponential and log domain and range, they have to swap too. So just like the exponential domain was always positive infinity to negative infinity, now it's got to swap. The y values are always going to be positive infinity to negative infinity for logarithms. Our end behavior, we can still use our pattern as we go all the way to the left. The farthest we can go left is our asymptote, 0. Where is our function existing? Our function is pointing downwards towards negative infinity. As we move to the right, we can keep going forever and ever and ever in the right direction. And our function is slowly growing upwards towards positive infinity. Notice that the same pattern we noticed last time. The farthest left is part of the domain. Farthest up is part of the range. Furthest to the right is our domain. And how far up is a part of our range. Let's do another example. Here's our graph. You have to figure out where it's flattening out. It's flattening out vertically. Right here. Where? Look at the x-axis. See how we're right at negative 3 on the x-axis? That's how I know it's x equals negative 3. So that must mean that we shifted our entire graph to the left 3 units. Now again, since I can tell I only go over to the right 1 to be on my graph, I don't move up. I'm not moving up 1. I'm not moving down 1. I have no up or down movement right here. So I know that I don't have anything up or down because that point isn't anywhere else. No up or down. That's certainly going to help me when it comes to my equation. These are always going to be log base 2 for the purpose of this video. And since we moved it to the left 3, means we're going to have plus 3 next to x. And since we did not move it up or down, that means we're going to have plus 0 on the outside. So really, our equation of our logarithm is y is equal to log base 2 of x plus 3. The domain, farthest x we can go, you got to stop at that asymptote, negative 3, but it can keep going to the right towards positive infinity. Our range, nothing's stopping us all the way down to negative infinity and all the way up to positive infinity. Our end behavior, the furthest to the left we can go is our asymptote, negative 3. Where is our function pointing at negative 3? Well, it's pointing down towards negative infinity. And on the right, nothing's going to stop us moving to the right. To the right, we're fine. Where's our function headed? Our function is slowly but surely pointing upwards. Again, the domain, has a direct effect on our end behavior in multiple ways. I did this backwards. So the x value of the domain affects the x on the left, has a height of negative infinity. The maximum value of the domain affects the right end behavior, and the range affects how high it's going. Let's do another graph. Here's a logarithm. I know it's a logarithm based on the shape, but I need to know where is it flattening out. It's flattening out right here at x equals 1. That means our graph shifted to the right 1 unit. Notice that from here, go to the right 1. That's right on our graph. So we did not move up or down. No vertical shift happening here. So our equation is going to be log base 3 of x. Since we're moving to the right, we're going to say minus 1. And then no vertical shift, nothing up or down. So our equation ends up being y equals log base 3 of x minus 1. Domain, the farthest left we can go is our asymptote at 1, but we can go all the way to the right. Our range, nothing stopping us. We're going all the way down from negative infinity all the way up to the tippy top at positive infinity. And behavior, x can only go so far to the left. It can only go up to the asymptote of 1, x equals 1. But the y value, our function, f of x, y, is pointing down towards negative infinity, y'all. As we head to the right, the farthest right we can go is towards positive infinity. I want to know what is happening with the y value at positive infinity. Well, it's slowly increasing, so we have positive infinity. Again, the cool pattern where the domain and range affect the x and y values of our end behavior. Again, the x and y values of our end behavior. Let's do another graph. JK, LOL. Let's have an equation, come up with the information that we need, and then sketch a quick graph. So we have log base 2 of x plus 2. Let's describe what's going on. We've got x plus 2 right here. Inside parentheses, that's our input. X plus 2, if we were going to describe this in words, x plus 2, that means we're moving to the left 2 units. There's nothing chilling out here, so there's no up or down movement as well. No up or down movement. Since we're moving to the left 2, we have our asymptote is an x equals equation because it's vertical, negative 2. And we're going to put that in, negative 2. We're also going to put in no shifting up or down for marker so that we have an x and y axis to graph our logarithm. Now that we have our new x and y axis to graph our logarithm, this is like x, this is like y, always to the right 1 was what we did, no matter what. And the graph will follow the basic logarithm shape, just like that. The domain of this logarithm, now that we have a sketch, we can see that it is forced to only go to negative 2 on the left, but all the way to the right, the biggest x value is positive infinity. The smallest y value is negative infinity, and the largest y value is positive infinity because it points downward. The smallest y value, that's towards negative infinity, but it slowly, this is kind of like growing very slowly, pointing up towards positive infinity. Our end behavior describes the left. So the farthest left we can go is negative 2. And where's our graph headed? At negative 2, it's pointing down towards negative infinity. We also have end behavior notation for on the right. Furthest to the right, we can keep going forever towards positive infinity. And where's our graph going? It's slowly going up towards positive infinity as well. The domain affects your end behavior. The range affects your end behavior. Just for the x values, the domain affects the x values. Your range affects the y values. Here's another equation, log base 4 of x plus 3 plus 1. Let's describe it in words. We have x minus 3. That means we're moving to the right 3 units. And we're automatically going to throw in to the right 3 our vertical asymptote. Now, since we have plus 1 on the outside, that means that's a vertical shift. We are shifting our graph up 1 unit. So let's put that in there. So we have a new x and y axis. Regardless of the base of the logarithm, always from this like x, y axis, we go to the right 1 and follow our logarithm shape. Technically, this base is 4, so that means it has the regular logarithm shape. We do have an asymptote here. We have a vertical asymptote. X is equal to positive 3. And that affects our domain. The smallest x value we have is 3, and the biggest x value we have is infinity. The smallest y value we have is negative infinity, and the biggest y value we have is positive infinity. We can write this as inequalities if we want. And now we need to talk about end behavior. As we go to the left, the farthest left this graph exists is that asymptote. Where's the function heading? It's heading downwards towards negative infinity on the left. As we move all the way to the right, we can keep going all the way to a positive infinity, and our graph is slowly increasing towards positive infinity as well. The domain values affect the x for the end behavior. The range values affect the y. And it's kind of like the domain and range on the left side affect the left end behavior. The domain and range on the right side affect the right end behavior. Let's do, I think this may be the last one. Log base 3 of x plus 1 minus 2. Describe it in words. What is happening to this function? We have x plus 1 in parentheses, our input value. That means we are moving to the left 1 unit. Go ahead and put in your vertical asymptote at x equals negative 1 because we're crossing the x-axis at negative 1. We have minus 2, a vertical shift on the outside. That means we're going to move our shift move our graph down 2. That's our new xy axis, as we can see. And just take a peek at the base of the exponential. The base is 3, so always go to the right one from your xy axis. And since the base is 3, that's like a growth function. That means we're just going to keep our usual logarithmic shape, which looks like this. Our domain, the farthest on the left we can go, the smallest x value we have is -1. Biggest x value we have is positive infinity. Our lowest y value we have, it goes all the way to the bottom, -infinity. It continues all the way to the top towards positive infinity. And our end behavior on the left, the furthest we can go to the left is -1 in the x direction. Where's our function headed for the y, or f of x? It's headed down towards -infinity. As x goes all the way to the right, nothing stopping us, can go all the way to positive infinity. Our y value, our height of our function, is also slowly but surely increasing towards positive infinity. Again, the domain x values affect the x value on our left end behavior. The range affects the y values on the left end behavior. And vice versa for on the right. The domain on the right affects the right end behavior for x. The range on the right affects the end behavior on the right. Awesome. I hope these videos help you in preparing for the final.